the hierarchy problem. The fact that introducing an elementary scalar field in a quantum field theory is problematic because there is some radiative correction that basically pushes the mass, the natural mass of this Higgs boson to very high scale, to the highest scale that you have in your theory. And I will come back to that probably tomorrow, discussing in details exactly what is the hierarchy problem. Okay. And this poses a problem in the sense that this Higgs boson, as it is introduced in the Standard Model, is unnatural. You certainly need some huge constellation to maintain the weak scale at 100 GeV also. So this is the hierarchy. So this certainly usually calls for new physics. A new physics at the TeV scale, new physics at the TeV scale, to stabilize the mass of the Higgs boson, or to stabilize the wave of the Higgs. And of course, this new physics has some influence on the physics of the Higgs boson itself. For instance, if you look at the production of the Higgs, they are gluon fusion, there is some loops, so it's really some purely radiative effect that produces the Higgs boson. In the same way, the way the Higgs decays, it decays, one of the best channels to search for the Higgs is where the Higgs decays into gamma-gamma, which is also a radiative process. So this is the gluon that are contained inside the proton, okay? And you have the loop, typically dominantly the loop of the top quark that produces the Higgs, and the Higgs decays into two photons. So this means that here you will be sensitive to any new physics that will circulate also in the loop. So this means that this new physics actually could have a huge effect on the physics of the Higgs boson, on the way we want to search for it. So it's a kind of ironic, right? Because we say that the Higgs is really the source of the masses of the elementary particle. Nonetheless, the dominant process at the LHC to search for the Higgs boson only involves some massless particles, the gluon and the photon. So it's a purely radiative effect that really controls the physics of the Higgs. So the question is really whether the Higgs shows any departure from the Standard Model itself. And when you don't know anything about new physics, the first thing to do is basically to use effective Lagrangian. So this means that you can, assuming that the new physics is high enough, that there is a mass gap between the Standard Model, the Higgs, and any particle belonging to new physics, you can integrate out those new particles, those new degrees of freedom, and simply write some effective Lagrangian for the low energy degrees of freedom, namely for the Standard Model particles. So that's exactly what was done, for instance, with the Fermi theory, right? Fermi didn't know about the W, but he could write simply a 4 Fermi contact interaction among, let's say, the proton, the neutron, the electron, and the neutrino. So here is exactly the same thing. So we don't know what the new physics is, but you can integrate out this new physics. So this means that you will neglect all fluctuation of these new degrees of freedom, and doing that, you will simply generate interaction among the Standard Model degrees of freedom, the Standard Model particles. And to describe those interactions, you simply have to write a Lagrangian which is invariant under the Standard Model gauge group. So typically, some dimension 6 operator that are invariant on the SU3 cross SU2 cross U1. And you can start looking at really what are the constraints on the scale that suppress those dimension 6 operators. So for instance, you can write an operator that involves 3 quarks and 1 lepton. So that's a dimension 6 operator, right? Because each of the fermion has dimension 3 half, canonical dimension 3 half. So this means that this operator in your Lagrangian has to be suppressed by a scale which is lambda squared. And the question that you are asking is what are the constraints on this scale lambda? So of course you all know that such an operator actually will lead to a proton decay, right? You can start with a proton with 3 quarks, annihilate them, and generate a lepton in this case. And there is huge constraint, of course, from the proton lifetime, right? And this is telling you that typically that the scale lambda has to be bigger than something 10 to the 30 in TeV. So this means that you have no chance to directly probe or directly see the new degrees of freedom that will generate this dimension 6 operator. Because the mass of this new degrees of freedom has to be bigger than 10 to the 13 keV. So certainly the LHC is not powerful enough to produce this operator. And of course this operator is actually breaking the baryon number and the lepton number. So this means that it's a very bad idea actually to write an effective Lagrangian that violates those global symmetry of the Standard Model. Then there is other operators that are breaking the CP symmetry, like for instance this one, d bar S. So it's again dimension 6 operator, right? And this will induce some KK bar mixing and things like that. Again, it's a dimension 6, and there is some constraint on the mass difference between the meson, etc. And this is telling you that, all the flavor constraints are telling you that these kind of operators have to be suppressed by a scale which is larger than 1000 T. There is a less dangerous operator that affect only, let's say, the third generation, the third AD generation, like the B meson and things like that. So S bar, sigma mu nu, F mu nu, which is the field strength of the photon, times B, times X to make it an SU2 invariant. Right? And then, so again, a dimension 6 operator, so you suppress by lambda squared. And in this case, a scale that affects this operator that can give, for instance, that can give rise to B2S gamma. B2S gamma can be generated by this operator, and the constraint on this process is telling you that the scale lambda has to be bigger than something like 50 T. So you're getting close, but nonetheless there is still no hope to directly to have direct access to this new physics at the LHC or at any linear collider that can be built in the future. The situation is slightly different when you are looking at the Higgs sector or the electric sector, because then you can start writing some operators that can be suppressed by a lower scale, typically a scale of order 1 or 2 TeV, or even lower. So some operators, some new physics that you can directly probe these times at the LHC. So for instance, there is this operator, H bar sigma AH times W mu nu A times B mu nu. Okay. So this is certainly SU2 cross U1 invariant by construction. And this actually enters into all the electric precision data. This, when you go to the unitary gate, when you replace H by its vacuum expectation value, this operator simply gives you a kinetic mixing between W3 and B, or if you want a kinetic mixing between the photon and the Z. And this, of course, affects the propagation of the Z. And this is well tested by lab, well tested, but nonetheless, the scale that suppresses this operator can be of the order of a few T. We'll come back and give you some precise number later on. And this is actually what is called the S oblique parameter, or epsilon free. S or epsilon free. In the US, people are calling it S, and in Europe, usually people are calling it epsilon free. There is another operator which is also important for electric precision data, which is called the T parameter, epsilon 1. T or epsilon 1, which is H bar d mu H squared. So if you want, it's a kind of modification of the kinetic depth with the Higgs boson. So again, it's invariant under SU2 cross U1, SU3 because there is no color in this case, it's freely SU3 invariant. But again, it's dimension 6, it's suppressed by H squared. And it's basically the same kind of constraint. Lambda has to be of the order of a few T, 1 TeV. There is even another operator which is basically not constrained at all at the moment, which basically modifies only the Higgs self-interaction, so H to the 6. So you know that in the standard model, and we'll come back in a moment, you write this Higgs potential, right? In the standard model, the potential for the Higgs in the standard model is simply lambda times a squared minus b squared over 2. So it's a dimension 4 potential. We stop at dimension 4, but of course in an effective theory, you don't care about renormalizability. I mean, just an effective theory which is valid only up to a scale lambda, and you can add some dimension 6 operator. So in particular, I can write in the potential, I can write this operator, h to the 6. This is, of course, again invariant. Invariant on the SU2 cross U1 if you want. You can write it explicitly by h squared to the cube. H squared is invariant, it's the same quantity that appears in the potential of the standard model. And you simply take the 6 power of this 6. And the only effect of this term, in the effective Lagrangian, is to modify the Higgs self-interaction. And clearly this is something that there is no constraint at all. You don't know how the Higgs interact with itself. You have been barely able to produce one Higgs boson, but you certainly don't know how the Higgs interact with itself. So basically there is no constraint at all on the scale that supplies this dimension 6 operator. It can be even of the order of 100 of GeV. You wouldn't know it at all. So this means that really in the electric sector, particularly in the Higgs sector, there is good hope actually to find new physics. And this perfectly agrees with this picture that you expect really new physics at the TeV scale to solve the hierarchy problem. So everything is kind of consistent. Now, the goal is either to produce directly the new physics or to give really some constraint and to try to identify the scale of those operators. Yes?
Just give an example for students to break you and ask a question. Where do you test T parameter? What are the experimental values which tell you that it's of the order of 1 TeV?
I'll describe electric precision data in a moment, but basically, I mean, the effect, if you write this operator in the unitary gauge, the effect of this operator is simply to modify the relation between the Z mass and the W mass. Because here, actually, if you write exactly what the covariant derivative is, this operator will give an additional contribution to the Z mass that doesn't exist in the standard model. So you modify the Z, so this means that you are modifying the propagator of the Z boson. So in any kind of data where the Z boson enters, you will be sensitive to this operator. So this means that in all lab data, you will have access to this operator. Okay. So now maybe we can come back a little bit more about the standard model. So try to describe exactly what Higgs in the standard model is doing, actually. So you know that the standard model is a description of all the fundamental interactions on the elementary particle, and it is based really on a gauge principle, namely you just have to assume that the standard model is invariant under some local symmetry, and then you know everything, right? So you simply assume, you simply build the standard model by requiring that it is invariant under SU3 colors, QCD. Then the electric interaction, which is SU2 left, times U1 of hypercharge. And this is a dynamical principle, right? Gauge symmetry is a dynamical principle. Gauge symmetry is dynamical in the sense that you are really predicting some interaction. Usually you introduce some symmetry just to classify the particle. That's what is done in chemistry, for instance. But here in particle physics is much more powerful than that. You just assume that there is a symmetry, and then automatically you know what the interactions are. So that's a big advantage of really particle physics and the notion of symmetry in particle physics. So you predict some interaction, and those interactions are very well tested. For instance, when you look at 3-point interactions, the interaction among 3 particles, let's say 3 gauge boson, etc., that was tested at lab. Nonetheless, this symmetry is actually broken when you look at the 2-point function, when you are looking at the mass spectrum. Right? So you know, I guess you know, if you don't know, I can try to explain to you in a moment, that the electron is associated with a neutrino into a doublet of SU2. It is transforming as a doublet of the SU2 symmetry. So if the symmetry is an exact symmetry, then those 2 particles should have the same masses. But you certainly all know that the mass of the neutrino is certainly much smaller than the mass of the electron. We don't know for sure what the mass of the neutrino is, but we know for sure that it is much smaller than the mass of the electron. So this means that this symmetry, the SU2 symmetry, certainly has to be broken to account for this mass difference. It cannot be a symmetry of the mass spectrum. And the way to explain this mass difference is really to call for the spontaneous breaking of the symmetry, or if you want, the Higgs mechanism. So you are saying that this symmetry is a symmetry of your Lagrangian, but is not a symmetry which is realized in the vacuum. The vacuum is breaking the symmetry spontaneously. And the way to do that, as you probably know, the easiest way to do that is simply to introduce a scalar field, an Higgs doublet. So it's a doublet under this SU2 symmetry, and it also has an hypercharge, which is equal to 1/2, let's say. And this Higgs doublet actually acquires a vacuum expectation value in such a way that in the vacuum, the Higgs is actually taking this form. There is a normalization, is arbitrary, of course. And this vacuum expectation value is not invariant under SU2 cross U1. It's only invariant under a subgroup of this symmetry. And if you look exactly at how the Higgs transforms, it transforms as a doublet, right? So H transforms as a doublet and hypercharge. And then you will realize that this vacuum expectation value only preserves a subgroup of SU2 cross U1, which is identified as the U1 of electromagnetism. So if you look at the action of this group on this Higgs doublet, you will see that the generator of T3 left of this SU2, so it's only a U1 of SU2 plus the hypercharge is actually what is called the electric charge, and it's Q, and this is the electric charge of this object is equal to 0. So the X is a doublet with an hypercharge 1/2. So T3 left is equal to -1/2 because it's a part which is the down part of the doublet, so -1/2. The hypercharge is equal to +1/2. So certainly this quantity has an electric charge which is equal to 0. So this means that this vacuum expectation value doesn't break the U1 of electromagnetism. So SU2 cross U1 is broken to U1 of electromagnetism in the vacuum. So SU2 cross U1 is a symmetry of the Lagrangian, but the vacuum is only invariant under a subgroup of this symmetry. And we can see that indeed this vacuum expectation value is actually generating some masses. So it is generating the mass for the quark on the left, and it's also generating the mass for the W and the Z, the gauge boson associated to the electroweak interaction. So how can you see that? Well, again, it's simply that in the Lagrangian, you have the kinetic term for the Higgs doublet. Okay? It's a dimension 4 operators in the Lagrangian, and it simply corresponds to the kinetic term. And because the Higgs is charged under the symmetry, here you have to introduce a covariant derivative. And this covariant derivative is the usual derivative, and then there is some interaction with the gauge field to make the theory invariant under SU2 plus U1. Okay. So it's E and G, W mu A, sigma A over 2 times H. So these are simply the generator of SU2. These are the Pauli matrices, right? SU2 generator. So, certainly no better than me. Sigma 1 should be 1, 1. Sigma 2 is I minus I. And sigma 3 is 1 minus 1. And you can check that those matrices form the SU2 algebra. And then there is, of course, minus I G prime. Then the hypercharge of the X, which is 1 half, divided by 2, and it's being so that's the kinetic, the covariant derivative for the X. And now you can see exactly what this kinetic term corresponds to in the vacuum. So in the vacuum, you see you can replace H by its vacuum expectation value in such a way that this kinetic term actually contains certainly something which is minus I G W3 minus I divided by 2 W3 mu plus G prime mu. It's minus G W3 mu minus G prime plus G prime. And here is G2 G W plus G W minus times simply V over square root of 2. Okay. So this means that when you take the square, you will actually generate some terms which are quadratic in the gauge field. And the piece which is quadratic in the gauge field simply corresponds to a mass term. The mass term is simply a piece which is quadratic in your field. Okay? Maybe W plus and W minus. Plus minus is simply 1 over square root of 2. W1 minus plus I. Okay. So you can write this mass term, and will give you something which is 1/4 G squared, V squared, W mu plus, W mu minus, plus 1/2 W3 mu, V mu. Here should be G squared, V squared, minus G prime, V squared, minus G prime, V squared, G prime squared, V squared times W3 mu. So you have one piece which is already diagonalized. If you want, this is simply the mass term for the W, for the charge W. So this is simply NW squared. The other piece is more complicated because it's not diagonalized yet, right? You have some off-diagonal mixing term between W3 and B. So this, you will have to diagonalize to find the mass eigenstate, and the mass eigenstate will correspond to the Z and the photon. But let us look a little bit more carefully about this matrix. So the first thing that you can notice is that first, he has a determinant which is vanishing. And this is not a surprise because you know that there is a symmetry which is unbroken, which is a U1 of electromagnetism. And this unbroken symmetry should correspond to a massless gauge field, and this massless gauge field is nothing else than the photon. Okay? So, call this matrix M squared. So M squared, G, V squared, or maybe I should put, here is probably 1 over 8. It's 1/4, so 1/2 will come for the normalization of the masses. Because for a real scalar field, the mass term is 1/2 m squared times the field squared. So the mass itself is 1/4 minus g prime v squared minus g prime v squared g prime squared v squared. So as I said, the determinant of m squared is equal to 0, right? G squared, G prime squared minus G squared, G prime squared, which is 0. So this means that you find the massless state, and this massless state is simply the photon. Okay, so you can also compute the trace of m squared, and since you have a photon, the other state will be the z, so it will correspond to the mass squared of the z, and this is simply 1/4 G squared plus G prime squared. The other thing that you can do also with these mass matrices is to compute the rotation that you need to perform to diagonalize it. And so you have a rotation, so namely you want to write W3 and B in terms of the mass eigenstate. So it's cosine of Z minus the sine cosine theta, sine theta of the photon, sine theta Z plus cosine theta of the photon. So you can check explicitly, it's just the exercise that sine theta is actually given the G prime divided by the square of G squared plus G prime. And this is called the weak mixing angle. So usually we put a W weak mixing angle or Weinberg angle, whatever it is. Weinberg was one of the first to actually introduce this mixing between W3 and B to give rise to the Z gauge pulse. Okay, so now we have obtained, which is important formula of the standard model, which is the mass of the Z, the massless photon, and the mixing angle. And there is one important quantity that you can compute out of those relations, which is called the rho parameter. The rho parameter is simply the ratio of the W mass divided by the Z mass squared and the cosine theta of the mixing angle. Okay. So let us compute that. So the mass of the W is 1/4 G squared times V squared. The mass of the Z is 1/4 G squared plus G prime squared, V squared, and cosine theta is simply G squared. So sine theta is G prime, so cosine, write it here, cosine theta W is just G divided by G squared plus G prime squared. Okay. So 1/4 G squared plus G prime squared, and then cosine squared, which is G squared divided by G squared plus G prime squared. Okay, so now we can simplify everything. G squared, V squared, Z squared, 1/4, 1/4. And this is equal to 1. So there is a theorem in theoretical physics which is telling you that every time after a long computation, you find a simple result which is 0 or 1. This means that either you have done a mistake in your computation or there is a reason why the result should be simple. So here clearly I haven't done any mistakes. This computation has been checked by many people. So this means that there should be an explanation why the rho parameter is equal to 1. So here, in the sense, it appears, as a miracle, associated to these matrices, etc. So it derived, basically it derived this result really using a particular realization of electric symmetry breaking, which is the one associated to the Higgs field. Okay, it seems that we have discovered Higgs field, but we still don't know exactly if the Higgs field that have been discovered there really belong to this Higgs doublet. We certainly have seen, you know, a scalar resonance which is coupled to the W, to the Z, to the quark, in particular to the top quark, via this loop. But we certainly don't know, and that's an important question which we are facing now. We certainly don't know if the Higgs belong to a doublet, like in this description. Here at the moment, this description in terms of Higgs doublet is purely, it's just a theory, right? It's just a very simple toy model. And it seems indeed that this toy model gives you this relation that the rho parameter is equal to 1, at least at 3 levels. So we would like to understand what is the deep reason of this region, of this result. And the deep reason is indeed a symmetry, which is called the custodial symmetry. So what is a custodial symmetry? Well, it's an hidden symmetry of the Standard Model. So I've told you that the Standard Model is invariant under SU3 cross SU2 cross U1, and this is a local symmetry, this is a gauge symmetry, but there is an additional global symmetry. And this additional global symmetry is really the reason why the rho parameter is equal to 1. Okay. So what is this symmetry? This symmetry is simply saying that instead of SU2 cross U1, which is a local symmetry, you have actually a bigger global symmetry, which is SU2 left cross SU2 right. How can I see it explicitly in my Lagrangian? I started with a Higgs field, right, which is a doublet under SU2. So doublet under this SU2 left symmetry. A doublet, it's a complex doublet, so it means that there is 4 real scalar fields. It's 2 and 2 in terms of the real degrees of freedom. 4 real scalar. And actually, if you look carefully at the Higgs potential that you're writing, this Higgs potential, which is lambda h squared minus v squared over 2 squared, this potential is actually invariant under the rotation of all these 4 real scalar fields. So there is an SO4 symmetry. And SO4 is actually nothing else than SU2 left cross SU2 right. So the way we can see it explicitly is that out of this doublet, you can actually construct another doublet, which is a complex conjugate. So I sigma 2H complex conjugate. And this is a property of the SU2 symmetry that SU2, the doublet is a pseudo-real representation. It means that the complex conjugate actually transforms in exactly the same way as the doublet itself. So this means that this H complex conjugate with this I sigma 2, which is the permutation, transforms exactly as the same way as H. So this means that you can build a 2 by 2 matrix by combining those two doublets, right? Because they have the same transformation property. So now you get really a 2 by 2 matrix. Right? Field phi is a 2 by 2 matrix. And the claim is that you can rewrite now this potential simply as lambda of 4, the trace of phi diagonal phi minus v squared. So certainly you can transform phi by applying the SU2 transformation, G left times phi. by construction, this potential will be invariant. Simply because this transform, the lambda to the 4, trace phi dagger will transform as phi dagger, g left dagger, and g left, and phi, minus v squared, which is constant, so it's invariant. And here you see that g left dagger and g left is just the identity by the SU2 property. Right? So you're using SU2 transformation, so g left dagger and g left is just identity. Okay? But there is also an additional symmetry, right? You can also transform phi by acting on the right. Phi right. So B 2 by 2 matrix, so you can apply a transformation on the left or on the right. And now, you transform this quantity as G right here, G right dagger. But clearly, because of the cyclicity invariance of the trace, G right and G right dagger will also be equal to the identity. So this will be invariant under the SU2 left plus SU2 right symmetry. Transform to itself. So this potential, the Higgs potential, is invariant under SU2 left cross SU2 right. So that's the invariance of the Lagrangian, the invariance of the potential. So now what is happening in the vacuum? Well, in the vacuum, here, I want to keep this piece. So in the vacuum, so I already say that H in the vacuum, the expectation value is 0, B divided by square root of 2. So this means that the vacuum expectation value of phi, this 2 by 2 matrix, is V square root of 2. So here it was H, so this is 0 and 1. And here it was the first column was simply H dagger times I sigma 2, which is 1 and 0. Okay. So here, if you remember, it's H complex conjugate, and then I sigma 2 is just basically changing the up and the down component. So this means that phi is proportional to the identity matrix in the vacuum. And phi transform as G left times phi and G right dagger. So clearly the vacuum is also invariant if you are performing the same transformation on the left and on the right. So if G left is equal to G right, then the vacuum is invariant. The identity matrix, if G left is equal to G right, this is an identity also. So we have discovered that in the vacuum, there is an unbroken symmetry, and this unbroken symmetry is the diagonal element of SU2 left cross SU2 right. So that's the symmetry of the Lagrangian, the symmetry of the potential, and in the vacuum, this is broken SU2 diagonal or SU2 vectorial. So that's the symmetry of the vacuum. So what does it mean? It means that in the vacuum, after electroweak symmetry breaking, I have an SU2 diagonal symmetry. And clearly under this SU2 symmetry, the free W transforms as a triplet. So this means that even if you don't know exactly the form of this mass matrix, if you assume that your theory possesses this SU2 custodial symmetry, so this is called a custodial symmetry. So whatever the realization of the Higgs, so now, I mean, the way I arrive to this symmetry is assume that indeed I have the Higgs doublet, etc. But now you can forget about this Higgs doublet. I'm just telling you, I just assume that my theory, whatever the theory is, should be invariant under this custodial symmetry in the vacuum. And then the consequence of this symmetry is that the W1, W2, and W3 in the vacuum should form a triplet of this SU2 symmetry. It should be a triplet of SU2 custodial, of SU2 diagonal, or vectorial, or whatever. So this means that if I write in the mass matrix that mix the W3 and the Z, so whatever it should be, here, the element here should be the mass of the W. Because I need the mass of the W here to form a triplet under the SU2 symmetry. So here I still don't know exactly what it is, so we call it Y, and Z. So that's the mass matrix in the basis, which is W3 and Z. So the SU2 custodial symmetry is telling you that this element has to be the mass of the W squared. And the other thing that you want to know, that you want to impose, is that certainly the determinant of this mass matrix should be equal to 0 to reproduce a massless photon. So the determinant of L squared should be equal to 0, which means that the mass of the W times Z minus Y squared is equal to 0. Yes?
Sorry, I've lost it a bit. That 2x2 matrix is the mass matrix for which pair of fields?
So W3 and U2. That's a mixing between W3.
Thank you.
So previously, I mean, we have seen a particular realization, with the Higgs doublet that was giving you this mass matrix. But okay, this realization was basically assuming that I really have the Higgs doublet, and I don't know yet in nature if indeed I have a Higgs doublet or not. So I want to derive some relation only based on symmetry. So I obtain this relation. And the claim is that these two properties, the custodial symmetry and the massless photon, or if you want the U1 electromagnetism invariance, are enough to basically derive that the rho parameter is equal to 1. Okay. So let us check that explicitly. By trying to diagonalize this matrix using this assumption that there is a massless photon. Okay, so here again I can write these kind of things. That I have W3 and B, which is related to the Z and the photon. And this means what? This means that so for the photon, we write that the mass of the W times minus sine theta plus Y times cos theta should be equal to 0. This is just telling you that the photon here, which is obtained by this relation, should be a massless particle. So it should be associated to a massless eigenvalue of this mass matrix. Okay? Is it clear? You have time W squared times minus sine theta plus Y times cos theta. And this has to be equal to 0. Okay? Which I can rewrite as the mass of the W to the fourth sine squared theta is equal to Y squared cos theta squared, and y squared, you can replace it y squared is mw plus z. It's cos theta. And what is z? Well, z you can compute the trace, right? So the trace of this mass matrix, trace of mw, is trace of m squared is mw squared plus z. Okay? And by definition, this has to be equal to mass of the z squared plus the mass of the photon, which is equal to 0. Okay? So z, you can replace z here simply by the mass of the z minus the mass of the w squared. Okay? So the relation that I obtain is what? Is that mw to the 4 sine squared theta is equal to mw squared mz squared minus mw squared times cos theta w. So let us simplify here with mass of the w squared, and you obtain mw squared sine squared theta plus cosine squared theta, which is 1. So the mass of the w squared is equal to the mass of the z squared times cos theta w. Which is nothing else than saying that the rho parameter is equal to 1. So what we have obtained here is that simply this relation that the rho parameter is equal to 1 is a simple consequence of the symmetry of the vacuum. That the vacuum is invariant under this SU2 diagonal symmetry. So you don't need to know exactly the details of this mass matrix, but what you know is that when you diagonalize this mass matrix, automatically the rho parameter is equal to 1. So that's a good prediction of any theory that satisfies custodial symmetry. And now if you take the number experimentally, these things have been measured, right? You know the mass of the W, you know the mass of the Z, you also know the cosine of the mixing angle. We'll describe that tomorrow. And you can check that the rho parameter is very close to 1 experimentally. So of course this is a 3-level computation, so you need to include all the radiative correction, etc. And this will account for the correction of the deviation from rho equal 1. So most likely, indeed, the nature, or if you want the symmetry of the vacuum of nature, is invariant under the custodial symmetry. So in any kind of model beyond the standard model, what you want to impose is your model automatically incorporates this custodial symmetry. And then you are sure that basically you are satisfying a lot of you are consistent with a lot of experimental constraints coming from rho equal 1. Okay, so I think my time is over. I'm running late. It takes a lot of time to write in the blackboard, and maybe tomorrow we'll discuss quickly electric precision data, because this is an important topic if you want to think about physics beyond the standard. So thanks a lot.
I'm sure there are questions.
Are there any additional consequences of the custodial symmetry? Except rho.
So there are of course some consequences when you are looking at the fermion. So you know, the fermion masses, the fermion coupling, etc. There is some residual consequences of the custodial symmetry. In principle, if the custodial symmetry were an exact symmetry, the top and the bottom should have the same mass, because you will have to be invariant under this SU2 diagonal symmetry, and this SU2 diagonal symmetry, the top and bottom will form doublet under this custodial symmetry. So this means that in the fermionic sector, the custodial symmetry has to be broken. So if you want this symmetry, I mean that's really how particle physics works. So if you have a symmetry in one sector, and then it is broken in another sector. And And that's why sometimes it's so difficult to identify some symmetry of nature, because it only relies in a particular sector. So here, for the fermionic sector, indeed the custodial symmetry will be broken. But there will be some consequences. So for instance, if you look at the radiative correction to the rho parameter which are induced by a loop of the top and the bottom, you will find some particular cancellation that occurs if the mass of the bottom were exactly equal to the mass of the top. So there are some further consequences beyond the tree-level relation. It's also true, and you can check the consistency of your expression at the loop level by going to the custodial limit of the loop hours.
Thank you.
And how can we measure rho parameter experimentally?
So that's what I wanted to tell you by discussing electric precision data. So certainly the mass of the W and the mass of the Z, I mean, that's easy. You just look at the mass of the particle, right? So you look at the bulk, etc. So you reconstruct the mass of the W. So the question is how you can measure the cosine of theta W. And for that, you can look, for instance, at the left-right symmetry decays of the Z. So the Z can decay into left-handed or right-handed particle. And by looking at the ratio of the two, basically, you have access to theta W. So there is some particular observable that allows you to measure cosine theta W, or sine theta W.
More questions? And if Higgs is in triplet, then there will be no custodial symmetry.
Yes, that's true. So if a triplet, I mean, you can compute the rho parameter for a triplet and you won't find equal to 1. I don't remember off the top of my head, I can give you the formula tomorrow. What is exactly the value of rho if you are breaking SU2 plus U1 by a triplet instead of a doublet? So this means that probably the Higgs is not a triplet and it's not part of a triplet.
If you have two doublets.
Two doublets? So two doublet is very interesting indeed, because the first doublet, so here we start with SU2 plus SU2, so which is SO4. In one doublet we break SO4 to SO3, and SO3 is the SU2 diagonal, so it's a custodial symmetry. Now in principle, the second Higgs doublet doesn't have to be aligned with the first one, and you can break SO3 down to SO2. But actually, in the motional 2 Higgs doublet model, this is not what is happening, and you can write the motional potential for 2 Higgs doublet model, and there is no breaking of the custodial symmetry in 2 Higgs doublet model. For some reason that I haven't totally understood yet. Or let's say you could break actually. I think the correct statement is that you could break the custodial symmetry, but if you break the custodial symmetry, you will break U1 electromagnetism at the same time.